Right, so we want to talk a little bit about the motion of falling bodies and exactly how these things move. We've already looked at the acceleration due to gravity, and we've seen that any body that is falling accelerates downwards at the same rate, irrespective of its mass. And the rate at which it accelerates is called g, the acceleration due to gravity, and we had a look at the fact that that is 9.8 meters per second squared. So we want to explore this value of 9.8 meters per second squared a little bit and see what in fact it means. I think the best way to understand it is that it means basically that every second the object is going to go 9 meters per second faster than it was the second before. Alright, so I've got a little example here to help us work through that. Imagine you've got an object that is dropping. So there's an object that's falling down and you took a photo of it every second. Okay. You would notice obviously in the first second it would go a certain distance, but in the next second, because it's speeding up, it goes further. In the next second, because it's speeding up, it goes even further. Right? And so you'd expect the distance that it fell in every second to increase. Now let's assume maybe that it fell 5 meters in the first second, and then by the end of the second, its total distance from where it started was now 20 meters. In other words, in the second second it fell 15. And then by the end of the third second, it had fallen 45 meters, right? And which means it fell, you can work it out, 30 meters in the third second, and so on. I've just used these numbers for a particular reason. You'll see why in a minute. But let's say now at the end of 1, 2, 3, 4 seconds, it's fallen a total of 80 meters. So if you were filming that or photographing that and you had those values, you could put them in a table. So here's your time values, and after 1 second it done 5 meters, after 2 seconds it done 20, etc, etc. Right, let's think about what the average velocity is. You may remember that to work out average velocity, there is a formula, and you would say delta x over delta t, which is basically displacement over time. Well, the displacement of this object is 5 meters in 1 second. So if you're working out the average velocity, you'd say 5 divided by 1, which equals 5. That would be 5 meters per second. Similarly, in the second, by the end of the second, he's done 20 meters, and it's taken him 2 seconds, so that would be 10. And you can keep going. 45 meters in 3 seconds is obviously 15. So you can see what's happening. His average velocity is increasing by 5 meters per second every second. So there we go. Average velocity increases at 5 meters per second every second, 10, 15, 20, 25, 30. Right, well, if that's his average velocity in that second, what was his instantaneous velocity at 1 second? If you think about his velocity values, if he starts with a velocity of, if you're looking at his velocity, if he starts with 0 and at the end of 1 second, his average across the 1 second is 5 meters per second, then at the end of that 1 second, he was probably doing double that. He was probably doing 10. There is a way to work it out, but your average velocity over an interval would be half the velocity at the end of that interval if you were speeding up consistently. If you think about it another way, if his velocity was 0 and it was moving up and it finally got to 10, where would he be doing after 1 second? If that was 1 second over there, where would he be doing 5? Would he be doing 5 halfway? So think about this interval. Okay, let's look at this interval here. We're going from 1 to 2 seconds. His average velocity over 1 to 2 seconds was 10 meters per second. But that means he would actually be doing 10 meters per second at the halfway point. So he'd be doing 10 meters per second at the halfway point to 2 seconds, and the halfway point to 2 seconds is 1. So he'd be doing 10. His instantaneous velocity would be 10 at 1 second. Similarly, if you think from 0 to 4 seconds, that's an interval. Well, his average velocity over 0 to 4 seconds is 20. Where would he actually be doing 20? At the halfway point to 4, or the halfway point to 4 is 2. So his actual velocity would be 20 at 2. Here's another interval, go down to 6. 6 seconds, 0 to 6 seconds. Average velocity 30 meters per second. Well, where would he be actually doing 30 meters per second? At the halfway point. Halfway point to 6 is 3. So 30 would be there. And you can now see what's happening. Every second his velocity, his instantaneous velocity, is actually increasing by 10 meters per second. So we can put it like that. Every second he's now going 10 meters per second faster than he was. So what's his acceleration? Well, acceleration is change in velocity divided by time. You can say, acceleration is equal to delta v over delta t. Well, let's do that here. What was his velocity here? 10. So you take final minus initial. 10 minus 0 over 1 second. Oopsie, sorry about that. That's going to be 10. What's his velocity here? Well, you're going to say, okay, it's going to be 20 minus the velocity that he was doing there, which is 10, divided by this 1 second. 20 minus 10 is 10. 10 divided by 1 is 10. And so you can now see the table looks like this. Every second his instantaneous velocity increased by 10 meters per second. And so his acceleration, we say, is 10 meters per second squared. What does that mean? His velocity increased by 10 meters per second. The object falls 10 meters per second faster every second. And that's what, we've used values that give us 10, but in actual fact we know the correct value is 9.8 meters per second squared. What does meters per second squared mean? Well, it means 9.8 meters per second faster every second. Hope that helps.